Okay, good morning again. So today we will be going through logic circuits, and we will first try to see the elements which makes those circuits also. So we have seen that we need to make an inverter, for example. And then our function is, the required thing is that if the input is low, output is supposed to be high. If the input is high, output is supposed to be low voltage. So how can we implement this? So this is inside. We will be deciding on that. And then, that's called logic family. And we can make this with diodes only, or resistor transistor logic, or we can make those with combination of diodes and transistors, which is going to be called diode transistor logic or TTL logic, or we can use MOS type of transistors, and those are going to be NMOS based families or CMOS, and there are going to be some other types that we will be seeing interesting devices. So how can we implement inside of that circuit so that low and high, are going to be created depending on the input? So this can be applied to an inverter, or it can be applied to a, NAND gate or NOR gate. So how can we implement all these things? Okay, so that's the basic idea. First, there is something called diode logic. Diode logic is something that's not used. It's not very efficient also, but it's worth to mention, because if somebody talks about diode logic now, at least you need to know about this. As you know, the diode, the symbol is shown like this, and then this is the plus side of this thing. So we call this thing V diode, and then the current through here is called I diode. And you know that the current or characteristics of this is like this. Oops. This is I diode. V diode characteristic is something like this. And this is how you see the response. And then if you apply a negative voltage, then there's going to be also a slight current here. And this current is called IS, minus IS. And then, we have seen this in detail in your previous courses, right? So we say that the voltage that is coming here is called the diode on voltage, for example. We diode on voltage, and then that's the resistance that you have, or 1 over RO, the resistance of the diode. So, but for the digital circuits, we don't really care about some of these regions here. So we just are after the condition where this diode, we model them. Okay, most of the time in these digital circuits, we will be modeling the devices. So we'll be saying that the response is going to be like this. Okay, in the model, we'll be coming here, and then we'll be saying that this is the response. So we call this thing VD on, and then this is the digital model. So in the digital model, we say that, you know, for the diodes, if the current is on, you know, that's how we can represent it. So the current ID, if ID is larger than 0, we say that VD is equal to VD on. So the model becomes like this. So this is the diode model. It is like VD on. So normally, you know, if we had a resistance in here, we could add it. So if the slope was like this, we could add that resistance also, but we don't even care about that. Because for us, this is an element either turning on or turning off. So if VD is less than VD on, we say that ID is equal to 0. So the model becomes like this. So no current is passing through here. So ID is equal to 0. Okay. So you know, considering this, we can make a logic circuit. So the diode logic can be implemented like this. First, maybe we can make an inverter, or not an inverter. Inverter is not possible here, for at least for this type. Let's see what it comes out here. So if the A input and B input and then Z input, okay? So we can either write it like this as a logic or as a voltage, okay? So let me do it first, A, B, and Z, logic-wise. Let's call this thing VA, VB, and VZ, okay? So if the VA is 0 volt and VB is 0 volt, you know, if we apply here 0 volt and 0 volt, then there is a current path here, okay? So there's a current path, therefore this voltage, if this is 0 volt and this is 0 volt, this voltage becomes what? 0.7 volt, which is V diode on voltage. Okay. So therefore this is going to be 0.7 volts. Okay. So if any of them is high, the other one is low. Let's go to another maybe option. So let's say this voltage is 0. Okay, 0. Let's say this is 0, and this is 5 volt. Okay, or VDD. So if that's the case, then we know that therefore for this case, this is going to be 0, and this is going to be on because there's going to be current flow here. And then this voltage becomes again 0.7 volts. And then now this voltage is 5 volts. This voltage is, this is on. And then this voltage is 0.7 volts. So 0.7 volt, therefore the diode is off, right? It's reverse biased. But output is going to be 0.7 volts, okay? So if we apply here 5 volt and then apply here 0 volts, again, the output is going to be 0.7 volts. And then maybe let's select another color here and then the blue, okay? If we apply here 5 volts, and then if we apply is 5 volt, and then let's say this is 5 volt again. For this case, there is no current flow path. Therefore, both diodes are going to be off. So this will be off, and this will be off. And then output voltage is going to be what? No current is passing. Therefore, the voltage drop across R is 0 volt. Therefore, output is going to be 5 volt. So 5 volts and then 5 volt is going to give us 5 volt at the output. So we can convert that into logic. And then if we convert this everything to the logic, so we can write this, let's say here. So this is low and low output. We can call it low, and low high output is low. High low output is low, and then high high output is high. So if we look at this, anyone, you know, we can write this here. Any input low gives us output low. Okay. All inputs high results in output high. Okay. So therefore, this is a NAND gate, basically. This is NAND circuit, okay, NAND gate. And this is this circuit. Okay. Sorry,
Hocam,
not
AND gate olmuyor mu?
Yes, good, good. I was checking you, you know, if you are following or not. Okay, good. Thank you for these corrections. However, this is not used much because if we look at this, if we keep, let's say, connecting this to another circuit, another AND gate, and another AND gate, the voltage keeps increasing. So here there is no active element other than the diode. So when we apply here, let's say 0 volt, this becomes 0.7 volt. For the next gate, this is going to be 1.4 volt. Next gate, this is going to be 2.1 volt. And then next gate, it's going to be 2.8 volt. Because you know that in digital domain, we need to connect the gates together. Output of one is going to be connected to the input of another one. So, I mean, this is maybe low. This is low. We can say that this is low. This is maybe low. Okay, is this low? No, this is definitely low, not. Okay, so therefore, you know, connecting is not possible. So this is not practical. It is not practical to use this as a circuit. Okay, so that's not practical. Voltage keeps increasing. Okay, and the second thing is that not option is not possible, or inverter. Okay, inverter is not possible.
Hocam,
Yes.
could you re-explain why the VD on voltage is 0.7 volts? When the diodes are off, for example, in the first example?
For the first example, diode is not off, the diode is on.
Yeah, I'm sorry, the diodes are on, but why is it 0.7 volts instead of 0 volts?
Because this is 0.7 volts, right? So the model in the model. So let me do it again, just with one diode. Maybe it's easier to explain. So if this is 5 volt, this is R, and this is the diode. So what is this voltage? The diode is on. We say that when it's on, there's a current, right? I mean, now there's a current here. There's a current here. So I diode is larger than 0. I diode is larger than 0 means V diode is VD on, which is 0.7 volts.
Thank you, Hocam. I understand.
Sure. Okay. So that's the thing. So we can also make a NOR gate here, and this circuit. So this is basically, sorry, OR gate. Okay. OR means anyone is high. You know, you will have high at the output. Okay. So like this is the OR gate. Okay. A, B, and Z. Of course, when this is VDD, let's say 5 volt, this is going to be 4.3 volts because there's a path for current to flow. So, and then there's going to be voltage drop of 0.7 here. So this is going to be high again. So you can do this as an exercise, but you know, all of them are low. Output is going to be low because if this is 0, this is 0, then both diodes are off and the voltage here is going to be 0 volt because no current is coming here. Okay, so but again, like here, the voltage at the output keeps dropping from 5 to 4.3 and then next minus 0.5, 0.7. So it's not practical. So we skip this, okay? But it's at least, you know, worth to mention a few minutes about this. So more practical thing comes with resistor transistor logic. So resistor, we call it resistor because at the input there's a resistor, and then we call it a transistor logic because there's an active element here at the output, which is transistor. So there is also a resistor here, but we don't call it resistor, transistor, resistor logic. It's just input stage and output stage is called resistor transistor logic. Okay. So we mentioned about this in the past, and then you know, we can find out about the operation of this thing, but before finding out the operation, maybe it's better just to review the transistor basics here. Okay, we discussed about this in the past. You know, we said that the response is going to be like this, and then like, you know, maybe up to 0.7, this is going to be like that, and then this is going to be VCC initially, and then this will drop until transistor saturates, and then this is going to be saturating 0.2 volts, right? So, okay, and this value we need to find, let's say, okay. So this is V in, V out graph. But like, you know, before going into details, we can look at the NPN and PNP transistors and the basics of it. I think in your EE312 course, you have seen this device, how it's operating in very detailed way. Okay, so you know, we say that this is the device. In fact, maybe we will see the cross-sectional view of this device in actual implementation. But typically in the courses, we define this as a device like this, okay? Whereas in real life, maybe we create this by doing that. Okay, we make a region, diffuse region, and then another diffuse region, and then this is N plus, and then doping wise, this is going to be cross-sectional view of silicon, right? The silicon wafer. So and then this is P type region, and then in order to get a good contact to P region, we make P plus here, P plus, and then this is the N region and substrate, and then in order to get a good contact to N substrate, we make here N plus, and then in normal operation, then this is going to be maybe, now this is schematic view. This will be called collector because low doped. This is going to be base, and this is going to be highly doped. So this is going to be emitter. So highly doped, emitter, okay, and then base, and then the collector. Okay, so this is the way that we define, maybe for simplicity, and then this is kind of symbolic representation of the device. Okay, but this is the actual implementation. Okay, actual implementation is like this. In any case, the device, I think you learned how this is operating. You know, since these are the devices, this is like as if you have two back-to-back diodes. Okay, so these are the two back-to-back diodes, and then this is going to be, maybe I should put it to the other side. This is going to be called base, collector, and emitter. Okay, so normally, since there are these two back-to-back diodes, you cannot have a current through here. So a current through here is going to be 0 unless you do something about this. Okay, the default current is going to be 0. And here, the current from base can be only positive. Okay, so current through here can be I base is always either 0 or I base is larger than 0. Okay, so I base cannot be lower than 0 is not possible. Okay, so we can we'll see the details of this again soon, but we can also implement the same thing as a PNP device, and the in PNP device here again, like this time for the PNP, we can draw this and then say that this middle point is N, and then this is going to be emitter is going to be here, P plus, and then this is going to be P, and we can put here the base. Okay, so in this device, this is as if we have two back-to-back diodes again, but the diodes are as if they are placed like this. So we call this thing emitter, we call this thing collector. Okay, and for this device, the current flow, I mean here, I base only can be in this direction. Okay, I base is either, if it is in this direction, like shown here, either going to be 0 or I base is going to be like this, larger than 0. Okay, for this one. For this one, this is going to be, can be only negative. Okay, if the direction is like this. Okay, normally it should be like this. Okay, And the direction of the current is in this direction from the highly doped region to down. So therefore, for this device, for the P device or PNP device, we define the current direction down because it's going to be positive that way. Okay, so either like this, or we change the direction of the currents to be able to talk about positive currents. Okay, so this is kind of you know, an extra reminder device. So so we'll be using these you know, transistors for the operation and for the modeling also. We'll be modeling this device. So this is the normal BJT, and the current, you know, we define the emitter in this direction. Collector current is in this direction. So the way that the device operates, I think you learned the basics for this, and we will not go into these basics. You know, you remember the minority charges, majority charges, and like how a reverse biased collector base junction is formed to have proper operation. So now we'll be looking at the voltage transfer curve or voltage current characteristics of this device. So in this device, VBE and IC current or emitter current or IC current is related anyway, as you learned, is going to be giving us a response like this. And sorry, and it's not very proper, but, and then we call this voltage VBE on voltage. Again, it's like a diode voltage, and the current is changing like this. So if you look at the maybe in more detail, also we collector emitter versus I collector current graph, you will see that these are like this. So you will have a current like this depending on the I base 1. And if you keep increasing I base, but for the same I base, you will be coming and seeing that this is going to be something like this, maybe. Okay, and then if you look at the positive thing, if we increase I base 2, this is going to also increase, and then you will see that this is going to be the current. Okay, and then this is going to be increasing much more for I base 3, and then it's going to be like going like this. Okay, but this is very narrow. I mean, very narrow, in fact. So for this region, we call this region as the we call this thing the forward active region, and then this region is called saturation region, and then this region is called reverse active region. Okay. And then this region, we can maybe define it like this. This region is called cutoff. Okay. So if we look at all the operation regions, there are 4 operation regions here, as you see. But typically, we look at here, maybe we can call this thing again like the cutoff region. And if we say this is VCE versus IC graph, and then if you look at this maybe in more, you know, precisely, we'll be seeing that the current is going to be like this, and then there's going to be like this, and then this current is going to be keep increasing. So this is going to be I base 1, and then this current, the IC current related to that is going to be beta times I base 1. So if this is I base 2, this current is going to be called beta forward, maybe, times I base 2. And then if this is going to be I base 3, this current is going to be beta forward times I base 3. Okay, so that's how we define. I mean, you have seen this in detail in the past, so we are just reviewing this. So, you know, when we look at, you know, some secondary effects on the operation of this device, we say that this is the ideal case, but in the actual case, there's going to be an increase here. You know, why this happens, as you learned maybe in the operation, and when we look at this, if this is collector, emitter, and base, you know that this junction is reverse biased, and this junction is forward biased, forward active, and this junction is reverse active. And then if the voltage between collector and emitter increases, then this junction, you know, starts, reverse bias region becomes increased. Therefore, the current flow from here, the electrons are going to be moving more from here and then collected at the, you know, collector. The electrons going from here are going to be, you know, collected at the collector site much more. So therefore, you know, when you have this thing, there's in the actual case, when collector emitter voltage increases, there's going to be slight increase here. And then, as you know that we define this slope. Slope is going to be called 1/RO. Okay, and then you know, when we look at this device for different cases, this is going to be maybe here, and then when you have this thing, this is going to be like this, and the point where they all cross here is called early voltage. Okay, early voltage, and then it comes to this. And for practical purposes, we say that VA is typically is going to be about maybe 100 volts or so. And well, we keep using this in our you know, future operations. So you know, we said that there are 4 regions of operations here. We can model each of these regions. Cutoff region, we can model. Forward active, saturation, and reverse active regions can be modeled. Like the same way we did the modeling for the diode, we will be modeling them, and then for simplicity, we will be using those models. So, and we can first talk about the operations here in general, and then we will be using something called Eber small model, and they developed the model for the transistor for large signal operation. You know, these are going to be large signal operation. You know, when the signals that we are dealing with, voltages are high. So operation regions, we call it cutoff region. If both VBE is less than VBE on, which is like 0.7 volt, right? 0.7 volt. And then, so that means VBE junction is off. And then VBC is less than VBC on. For practical things, this is not going to be 0.7. This changes actually. So we can call this thing 0.6 volt or so. And then that means V, or not V, but BC, BC junction. So this should be BC also, sorry. BC junction is off. So therefore, you know, this device, both junctions are going to be off. So collector, base, and emitter. So we can, you know, look at this device like this. Basically, a diode junction and this diode junction, they are both off. Okay, this is off. This is off. This is base, collector, and emitter. Okay, so that's the case. Then all the currents that we talk about, like this current, IC is called. This current is called I emitter, and this current is called I base. They are all going to be zero. I base will be zero. I emitter will be zero. I collector is going to be zero. So that's the off case. Okay. So saturation region is both BE and BC junctions are on. So this time they are not off, but they are both on. So for this case, we will look at this VBE voltage. VBE voltage is going to be not VBE on. Instead of VBE on, we will be calling this like on. Will be, instead of this, we will be calling it saturation, because for this case, more current is passing from the base emitter junction. Therefore, as you remember the diode voltage, you know, characteristics here, like here also. So instead of using 0.7 here, maybe more current is passing. So we can say that the current here is going to be 0.8. So in the model, it's better to use that as 0.8 volt. So we call this thing 0.8 volt, and then VBC voltage is going to be equal to, because it's on, VBC SAT, and then that voltage is going to be, in practice, people measured this, and found out that this is it. And if this is the case, then we can look at the collector emitter voltage during the saturation case. It's going to be, you know, from the circuit we can find out. This is going to be, in fact, 0.2 volts. Let's just, we will be finding this later on, also in detail. In the forward active region, just quickly, BE junction is on, but BC is off. And for this case, we say that VBE voltage is going to be VBE on, and it's going to be 0.7 volt. And then for this case, the collector current is going to be equal to beta forward times. I mean, you remember this from your previous courses. I emitter current is going to be I base plus I collector. So, you know, this is the relation here. This is going to be 0.7 volt, and this is going to be I base, and the current through here is going to be beta forward times I base, and the current through here is going to be I base, so it's going to be 1 plus beta forward times I base. Okay, so that's quickly to remember, you know, it's coming from your previous courses. So I guess, you know, this is kind of summarizing the in forward active region. In the forward active region, what is happening here, and that's, I guess, we just summarized what is happening here. You know, VB is going to be equal to VB on, which is 0.7 volts. Collector current, in fact, is going to be equal to ICS e to the power VBE divided by VT. This VT is not threshold voltage. VT is this value, and that's how we can model it. So now this is the real model that we'll be using. Two people, Ebers and Moll, you know, developed this model. They say the transistors or diodes are not good representative of the device, because you know that in saturation there are more currents involved, for example, and then in forward active, you know, one diode is off, but still there's current coming. In forward active, for example, only this diode junction is on, but there's going to be current here still. You know, it goes through the device, and then this is beta F times I base, if this is I base. Okay, so how can we model this is drawn here. By the way, if you want, we can give a break, or we can just continue, because once I start explaining this, I want to continue to explain without an interruption. Shall we give a break or just continue for 10 minutes? What do you say?
Bence mola verelim hocam biraz.
Okay, let's give the break. An official break, okay? So we'll meet at 11:40. Is that okay?
Okay hocam.
Yes.
Teşekkürler.
Let's meet at 11:40 a.m. Okay. Can I interrupt recording? Recording pause. Merhabalar.
Merhaba hocam.
Merhaba hocam.
Okay, shall we start? Başlayalım.
Başlayalım hocam. Herkes burada.
Okay. We will be talking about EBR small model. We keep saying that the device is like this, actually, two back-to-back, diodes. But if we look at the other operation modes, this is going to be looking like, this diode, but as if there is another element here. So there is this diode, but there are other currents as involved because of the minority charges and then the way that we bias the devices. So these extra current points are going to be modeled with these extra elements like this, for example, and then this element. Okay, so when we do this, I guess it's going to be more clear soon if we go to the details what we mentioned. So the alpha F is something related with beta F. Forward current amplification factor is alpha F, and alpha R is like related with beta R. So if we look at the currents here, there's going to be a current through this diode phase emitter, but something related with that current is going to be flowing through here. Okay, so something related with that current is flowing in here, and similarly, current related with the this diode is going to be coming here. So this is going to be I D base collector currents. Okay, so if we do the model properly, then we will be able to obtain all the operation points properly. So we will call this current in this direction I diode base collector, which is this current I diode base collector. Okay, whereas let's call this one I diode base emitter is going to be this current I diode base emitter. So we will look at the device in all these different cases, and then we will be understanding why we add this second element here soon. So here for the first case, a cutoff case, we know that both diodes are off. So for the cutoff case, both are off. Okay. So if both are off, then we know that And this diode is off, so the current here is 0. Okay, current here is going to be, let's say, 0. And this current is going to be 0. If that current is 0, this current is 0, and then this is going to be 0, because this one is 0. And this is 0, there, that means this is going to be 0. So 0 amp, 0 amp, and 0 amp, 0 amp. And therefore, a current source with 0 current means open circuit. So you know that in the model, if the diode is off, the model is in the diode. If it is off, the diode is like this. But this one is off. Current source with 0 current. That means it's also off. Okay. Model. So basically, when we look at this, the model of the device is like this. And we know that this is the model anyway. So by adding these elements, these two elements, is not, conflicting with our model. So this element and this element, eventually, we know that for the cutoff mode, this is similar. Okay. So the current here, IC is equal to 0, IB is equal to 0, and I emitter is also equal to 0. Okay. So the model is representing correct for the cutoff. Okay. So we'll look at the model in forward active region. In the forward active region, let's look at it. We know that for forward active region, base emitter diode is going to be on. Okay, so maybe I should give a different color here. This is going to be on. So this is going to be on. Okay, but base collector is going to be off. Sorry. This is going to be off. So this will be off. Okay. So if this is on and that's the case, then you know that this current is going to be on. And that current is going to be, related with this current. So since this is off in the model, this is going to be this part, at least for the diode. This is going to be the case, but this will be, this one is going to be active. Okay, so therefore, this current will be 0. And if that current is IDBC is equal to 0, then this is going to be 0 also. So this is going to be, then we can ignore this. Okay. Can be cancelled. Okay. Current source with 0 current. Okay, so if this is the case, this is gone. This one is gone. This is gone. Okay. So what we will be having is in the model, it's going to be like this. The base emitter on, that's the diode model, and the current here. The current here is going to be related with base current. Okay, and that current, maybe it's just jumping into this. Maybe I should do this step by step. So, in fact, the model, maybe I should do it this way. The model will be like this. There's going to be a diode here. And then the base. And then there's going to be this current controlled current source. And this one is going to be alpha F I D B E. And this is I D B E. Okay, so this is the case. So if we replace this with the model of the diode, we said that the model of the diode can be like this. Right, this is 0.7 volt, and then there's going to be this element, and this element is what? This element is going to be current source. Okay. 0.7 volts. Here, I don't have space, so I'm trying to find a space to fit in here. You know that this current is of F IDBE is also equal to, now how am I going to jump into this, times IE, because this current is called I emitter current. So if you play with the numbers, and you have seen it here, what is alpha F? And if you put this into here, and then this is going to be equal to, at the same time, beta F times IB, which will be also equal to IC. So beta F times IB is, can be used for that current source. And now we can, switch that, the position of this diode is more convenient if it is shown like this. It's more convenient. So instead of here and here, okay, we can move it here. So if we move it here, is there going to be any change in the actual operation or the modeling? So in fact not. because what we care is voltages and currents. Okay, here, either here, okay, VB is same, because VBE in this model is going to be VBE on, which is 0.7 volts. So nothing changes in here. So in terms of current, IC doesn't change. Here it was IC. It is IC still. And IC is equal to beta F times I base. So, okay. I can put here check marks. What else I need to be same? I emitter. I emitter is also equal to I base plus I collector. So that's going to be beta forward plus 1 times I base. Okay, so this I emitter is also okay. So this is why we moved here from here to here. And what about the collector emitter voltage? Actually, collector emitter voltage, you know, when we move this here to here, is not affected because there's a current source here. You know that, note that, maybe I'm going to write it here. Note that if you have voltage source parallel to a current source, okay, and then you try to connect this to a resistor, which one is dominant? B source, I source. Which one is dominant? We can voltage source. So this can be cancelled, ignored. And then this is going to be similar to this one. Okay, V source. So similarly, if you have maybe, sorry, a voltage source, maybe I should put it the other way around. Current source and a voltage source. And then if you think that this is connected to a resistor, which one is dominant? Which one determines the current through the resistor?
Current source.
Current source. So then it doesn't matter here, can be ignored. Therefore, this is going to be a current source or resistor. Okay. So this is the reason why we have having here this one and then removing this to here is not affecting our operation, because here the current is determined by the current source, and in the other one the voltage is determined by voltage source anyway. So therefore this model is also correct and then satisfy our operation. So therefore we will be using eventually and finally, this will be our model for the forward active. This is going to be emitter base 0.7 volt and the current controlled current source, and the value is beta F times I base, and this is I base. Okay, from either small model, we achieve this. And this is the convenient way of representing the transistor. Okay, so this is the eventual model. Is that okay? Okay, so the third case is the saturation case. In the saturation, as you know, both of the devices are on. So this one is on, this one is on. Okay. So if they are on, as we mentioned here, if there is a voltage source parallel with current source, what do we ignore? This can be ignored, right? Why? Because voltage source parallel with current source and resistor. Okay. Voltage source dominates. This can be ignored. And here also this can be ignored. So therefore, our model reduces to this. A voltage only. And then this voltage. And we say that this voltage and that voltage, in practice, we found out that this is like 0.8 volt and this is 0.6 volt. Okay. So if this is the case, we like to, again, maybe, move this somewhere else. Like move it here. And then move this, because now it's voltage source, we cannot ignore it. And then move to this branch. If we do that, then this is going to be 0.8 volt here, 0.8 volt here, 0.6 volt here. Eventually, we can reduce the model to this. This is going to be 0.8 volt, and this is going to be 0.2 volt. And this is, again, consistent with our B collector emitter in the saturation model. Okay. So BJT sub model is going to be this. This will be our, maybe I should do it this color here. BJT SOT model. So the last model for the transistor is going to be reverse active model. Now the reverse active model, in the reverse active, we say that this junction is on, but this junction is off. Okay, so this one is off, this one is on. And since this is on, this is going to be replaced with a voltage source. And then this will be coming in parallel. A voltage source and current source can be ignored. Okay. And since this is off, this is also gone. Therefore, we'll have only this one, alpha RIC. But if you rearrange this, this will be beta R times I base. And the voltage here is going to be C on. And for this case, the voltage, this is going to be good enough current, maybe. It's going to be 0.7 volts. So for the practical purposes, we like to move this to here. And if we move that to here, nothing will change. And the voltage here is going to be like this now. Current and voltage 0.7 volts. And this will be in the model. And then we know that the current direction is the other way around. So eventually we do this for the model. For the reverse active region, this is what we do. We consider this as if somebody make a mistake, and then after that mistake, this looks like again BJT. This is the base to collector on, and then 0.7 volts. But here, the value here is going to be beta R times I base, and this current is I base, and the current here is, what was this node? Was emitter, right? So this is emitter. Now I call this thing emitter current, but the direction is reversed. And then this current is collector. I call it collector current, but the direction is reversed. And now the emitter acts like a bad collector, okay? Because remember, emitter was highly doped, collector was low doped. So we switched and the elements, and then right now the device looks similar, but now instead of this is N plus, this is P, and this is N. Therefore, it still looks like BJT, but with a burst beta. Beta R is much smaller than beta F. Beta R is much smaller than beta F, okay? But here, the current in this direction is going to be, if this is I base, this is going to be I base times, instead of beta F, now I am calling it beta R. And here, the current is I base times beta R plus I base. So, or another way of beta R plus 1 times I base. So it will be more convenient to use this way, and then we will not be confused. So when you look at the element and device, this is going to be the model that we will be using it. Any question? So now we need to look at this, what we did. by this modeling. Now, if you look at the actual operation, in the actual operation, we said that there are going to be this maybe this will be the operation. So the current is going to be like this, and then there's going to be like this. Maybe I'll draw one more. And then in this operation region, okay. So if this this is I base 1, this will be beta forward times I base 1. And if that's the case, then this current is going to be 1 plus beta R times I base 1. The collector current here is going to be in the other direction, so it's minus sign. Maybe I should put minus here, because the direction is the other way around. Okay. Let me do it again. Is that okay? And this is, let's say, I base 2. This will be beta f times I base 2. And this value, whatever it is going to be minus 1 plus beta R times I base 2. But more than this, what we did with in this model is like this. Now this will be very tricky. Now, what we ended up doing is in the model, we say up to here, this is going to be our model. Our model says you have this, and our model says you have this. So this is the voltage, 0.2 volts. So collector emitter voltage in forward active region is going to be modeled like that. And this is the SAT region. And in the model, we make this thing, flat, and then flat, and then flat again. But here, I mean, there's a problem here, there's a problem here. What do we do here? So this region is really, is not a correct region. So here in the model, we assume that this is like this, okay? And then this region, not properly modeled. Okay, because in the correct operation, I mean, in the modeling, maybe we should have done this one here, and then here, and then here. But for the things that we already did, what we did was we connected this, okay? So a very small model, and then the thing was given like this. Okay, so we don't really care about this, but you will see that this mistake or in the modeling will create a problem later on for us. Okay, sometimes you'll say, oh, what is happening here? You know, when we go from SAT to reverse active, there will be problems. So this is reverse active region. Okay, there's no problem with the off region. So here, the blue ones are digital model of the BJT transistor according to the reverse model. Okay. Reverse active. So the reverse active going from SAT to reverse active and vice versa, or reverse. Other way around. Can create conflicts with what we know. Confusion. Okay, so, but what we will say is that this is due to the confusion, and then we will ignore it. I mean, this is due to the modeling that we did. So basically, we will assume that this is going to be transistor model. Okay. And then my collector, a collector emitter. This will be the case here. Okay. Is that clear? And then this region is going to be not very clear. Okay. So if we look at really the real case for the transistor, in fact, the real case is like this. This is the real transistor operation. I mean, this is going to be like coming like this, and then here, and then this is how it goes. And this voltage here, normally, this voltage is about 50 millivolts, the cross section. IC, V, collector emitter. And, you know, if we take this diode and then use it in, expose it to sunlight, then, you know, this region actually 50 milliwatt region changes, and then that's how we create solar cells. But typically, you know, this is the really the case. And But modeling it maybe differently is going to create one other thing, and we'll have to say reverse SAT, forward active SAT. Those definitions will be more critical or create issues. But I mean, as long as we know that there's a problem with the modeling at that region, then but we will be over there only very small portion of the time. So we will be mostly using a very small model very comfortably. Okay, so therefore, coming back to BJT operation regions, to understand if the transistor is off, cutoff, check base emitter voltage. If it is less than 0.7, and check base collector. If it is less than 0.7, then you say that the transistor is in the cutoff case. For the forward active region, to understand if a transistor is in the forward active region, what you do is, set this voltage to 0.7 volts. Check the collector emitter when, setting, because we will assume it's forward active. As you know, the collector voltage collector current relation is like this. Okay, so if maybe this is wrong, let me correct this. If this was larger than VC is SAT, which is 0.2 volt, then we can say that transistor is in forward active mode in its forward active mode. Okay, so that's how we will be determining the state of the transistor. For the saturation region, we will set the collector emitter maybe to SAT voltage. We collector emitter to the collector emitter SAT voltage, which is 0.2 volts. And then we will be finding IC and IB, and then check if IC is less than beta F times IB. Why is this the case? Because in normal operation, we say that this is going to be the value, and this is IC, this is VCE. If in normal operation, we say that this one is equal to I base, and this is equal to beta forward times I base. Okay, so if the value that we find is here, okay, so if IC that we find here, IC, if IC is less than beta F IB, then in saturation region. Therefore, that's what we do here. If it is less than beta Fi base, then we are sure that it is in the saturation region. For the reverse active region, we can look at V base to collector on. So this V base to collector on, either we check it for 0.7 volt or maybe 0.5 or 0.6 volt is okay. And for this case, if the base emitter is less than 0.7, then we know that I emitter is going to be equal to, the direction is important here, beta R times I base. Okay, so this one is I emitter. Direction is the other way around. Okay, so here we'll draw the transistor like this. And this is emitter. This is collector, and I emitter is this direction. Okay, and then when you try to find the state of the transistor, because why do we do this? Because there will be more than one transistor, in fact, in the circuit. So we need to look at the cases for the transistor. I base direction can be only towards spelling mistake, towards the transistor. Transistor for NPN. NPN. Okay, so if you have an NPN, if you assume a state for the case, and then if this is negative, then you know that your assumption is not correct. So for the maybe if the transistor is PNP, for a PNP transistor, I base can be only out of the device. Okay. So one other thing, this is maybe one. Second point is the digital model is very rough. In some cases, and rough, and can create results at the boundaries. Okay, especially when you go from SAT to reverse SAC or vice versa. Okay, these directions there might be some problems. Okay, so I guess now we finished the modeling. Wow, it took a long time, this modeling, but the time is up. So we will look at this from a real example, how we can get the voltage transfer characteristic of this device. Okay, so we will look at the cases here. First, how to understand the state of the transistor. That's what we will look at it. I mean, we can check this, for example, element, and what is the state of transistor. Now we will look at this junction, possibility of this junction, and this junction. And for example, here, there's a path that current can flow from VCC to here. Therefore, this junction, we know that VBE should be on. If it's on, we know that transistor off case cannot be. And then if that is on, we know that maybe transistor is either or reverse active, not possible. Okay, so therefore Q, transistor, let's call it Q, is either SAT or forward active. Okay, so which one? We will assume one, let's say forward active, and check these conditions mentioned in the previous version. Okay, and that's how we will be determining the state of the transistor. Okay, so is this junction, this is on for sure, this is, we don't know, and depending on that, it's going to be either in SAT or forward active. We will be finding this next time. Okay, let's stop it here. Okay, I think the time is up, so I like to stop it here. Any questions?